Friday. So I showed it today. Lucia. Do it today and watch football tomorrow. Just finish today and then go with love or watch football. Look for Razorman. Do we have any hope this semester? No, not yet. Long time ago we were like the top 10 or we were 2011 maybe it was like the fifth. We ranked like the 5. I never looked at hope. But anyway, Janet, we are waiting for you. So, homework is available, as I said. We will talk about that very similar to homework questions. So when you do homework, please use that homework documentation, not this slide. I changed the numbers. The homework will be a little different from what we look at during class time. And we are looking at cyclohexane production via benzene hydrogenation with recycled streams. What are the key points here? We are looking at cyclohexane production. Okay? By reaction, it's called benzene hydrogenation. Benzene hydrogenation means benzene reacts with hydrogen and produce cyclohexane. You are Jacob?
Yes.
Wow. Welcome to this class. You are attending first time. Jacob, I checked your attendance. So you didn't draw. Okay, welcome. I checked every time for your attendance. So you actually showed the first time. Welcome to this class. Jacob, did you submit homework? No, I see. Okay. So homework is available. Homework 3, the due is next Friday. Anyway, so our topic is cyclohexane production through benzene react with hydrogen produce cyclohexane. Benzene hydrogenation with recycled streams. We will learn the new thing, recycled streams. How do we handle? How do we deal with these recycled streams? That's a key point. Cyclohexane production through benzene hydrogenation with recycled streams. Cyclohexane produced through 1 molecule of benzene react with 3 molecules of hydrogen and produce 1 molecule of cyclohexane. In other words, 1 mole of benzene react with 3 moles of hydrogen and produce 1 mole of cyclohexane. This reaction is highly exothermic, as you can see. So enthalpy change is negative 217 kilojoule per mole. And cyclohexane is used for the industrial production of adipic acid and caprolactam, which are precursors to nylon. So cyclohexane is also precursor to produce nylon. Chevron Phillips Chemical, so the company name, Chevron and Phillips, a joint company, produce high purity. How high? 99.9% purity. 99.9% purity cyclohexane at this chemical complex in Port Arthur, Texas. Who is from Texas? Oh, Allah. Do you know where Port Arthur is? Can you explain us where is Port Arthur? From Houston.
It's like right between there.
Okay. So from Houston, Louisiana, if you drive from Houston, okay, you drive I-10 to eastbound to the Louisiana side. Now eastbound, you drive about 1 hour 20 minutes. It's called Port Arthur, Texas. Yeah? There's huge chemical complex. Port Necho, Port Arthur, not only Chevron Phillips Chemical, there's a refinery, there's fertilizer manufacturing company there, a lot if you are interested in, maybe you can apply send your resume to this chemical company. But anyway, Chevron Phillips Chemical produce high purity cyclohexane in molten azo hexane complexane. How high purity? 99.9% purity. Why they produce 99.9% purity? Then I write the very sensible. Because consumer demand. To meet consumers, consumers are looking for 99.9% purity to meet consumers demand. Yes. Process description, let's look at it very wordy, but anyway, hydrogen benzene react produce cyclohexane. What kind of react we are using? We are going to use R-stoic reactor, stoichiometric based reactor. So last Wednesday we looked at reactors. Who practiced to look at reactors? Wonderful. Okay. What kind of reactors did you practice? Claire? Huh? R-stoic. Yeah? That's all? So we practiced the 5 different reactions. Do you remember? Or you don't remember? Does anybody remember 5 reactors we practiced the last Wednesday class? Come on.
R
Look,
plug.
yes. R plug. Plug flow reactor. R plug reactor.
RCST.
RCSTR. Can you explain us what is RCSTR? Come on.
It's a continuous stir tank reactor.
Wonderful. Excellent. Come on, continue.
Yeah, R gives.
R gives.
I can't remember the name.
Batch reactor. Clear is clear now? Yeah. Nothing special. So we look at it 5 different reactors. Now we use R-stoic reactor today. Yes, so please spend some time to look at different reactors. And so we are working on using R-stoic today. Our topic is though, we want to look at some recycled streams, how to handle the recycled streams. So if you look at this process flow sheet, as you can see, we have somehow recycled streams. How do we handle these recycled streams in process simulator? That's the topic today. As you can see, okay, we feed these 2 feed stream to preheat our heater to increase the temperature to reach some reaction temperature. And the reactor effluent stream is then sent to flash separator. Oh, we use a flash separator. Of course, flash separation is to separate vapor phase and liquid phase. Okay? And then vapor stream coming off the flash tank is recycled back to the feed mixture after a small amount of purge stream is removed, okay, to prevent any impurity build-up in the system. So we use some purge stream to remove any impurity building up in the system. Most of the liquid stream leaving the flash tank goes to a distillation column. Why we use the distillation column? Where we will get some cyclohexane product from the bottom stream of the flash separation, but that stream does not have the purity we are looking for. So we install another unit block, it's called distillation column, to meet consumers' demand, which is 99.9 mole% purity. While a small amount of liquid stream is recycled back, why we recycle back? We don't want to lose any valuable product within that stream. In this case, benzene. So we don't want to lose that benzene. We recycle back to the feed stream so that we can use that benzene stream again. Questions are, what property method did you choose? That's the first question. How can we find out? In Aspen, you can choose method assistant. And method assistant will recommend you several different property methods. Then you can answer the first question by trying those several different property methods. What property method did you choose? What is the maximum RFLIQ? What is this stream? I just named it this way. This stream is product stream in distillation column. So this is the bottom stream from the distillation column. Bottom stream. We get cyclohexane from the bottom stream of the distillation column. What is the question? What is the maximum cyclohexane production rate from the bottom stream of the distillation column with purity of 99.9 mole %? Looks like Clara understood. Clara, can you rephrase? Brian. Okay. Very good. Brian, can you help us by rephrasing? What is our task or objective today?
Maximum RF.
What? Can anyone volunteer to explain what is our objective? So I am looking at what is the question. Anyone? Yeah, Chase.
Consumer demand is 99.9 mole %. Like, what is the most we can get out of the distillation column and meet that demand? What's the most suffix that we can get out? The most of the highest rate.
We try to get the maximum cyclohexane production rate. That's what we are trying to make. So our objective is here to get maximum cyclohexane production rate. Why? As a company. What was the company? Chevron Phillips. They want to produce the maximum cyclohexane production rate. They want to get the maximum cyclohexane production rate. From which stream? Bottom stream of the distillation column. But consumers' demand is 99.9%. So this is fixed value. 99.9 mole % purity is fixed. We cannot change. What we are looking for here, we are looking for maximum cyclohexane production rate from the bottom stream of the distillation column with purity of 99.9%. Show your answers with red circles on the process flow sheet page, including a stream table result. So if you look at this process flow sheet, we have the hydrogen feed stream, benzene feed stream is fed through this called heater. So this unit flow we look at is called heater. We can use as heater or we can use as cooler too. Okay? Why preheat or heater is used? So we want to increase this low feed stream temperature to reaction temperature. We use R-fluid reactor. In this reactor, as I said, one molecule of benzene reacts with 3 molecules of hydrogen, produce 1 molecule of cyclohexane. Remember that one? Then we will have some vapor liquid mixture from this effluent stream of the reactor. So we use flash separator to separate vapor phase and liquid phase. As you can see, in the vapor phase, we have some purge stream to prevent any impurity buildup in the system. And we also recycle back to the feed stream. We don't know what percentage or amount, but let's see. And then liquid stream from the flash separator, a certain amount of this liquid stream is sent to distillation column to purify the feed stream. And certain amount of this liquid stream from flash separator is recycled back to the feed stream. Our target is to get maximum cyclohexane from this bottom stream of distillation column, but another important objective here is to learn how to deal with recycled streams in process simulation. Yes. How to handle recycled streams are not that easy. So we will spend some time today to look at it, and we'll spend more time next Monday to look at in the recycled streams. So I give you some time to practice today or during the weekend, and then we can look at it next Monday again, little in depth of recycled streams. Now all information is given, feed stream input specifications are given, and the heater input specifications are given. If you look at your reactor, okay, stoichiometry given, conversion rate is given, and some information is given. It's called pressure drop. So far we used to have pressure itself. Now the information pressure drop is given. How to handle this pressure drop, given information in past tense later on. And flash tank, the temperature is given, also pressure drop information is given, how we use this information for simulation. And purge stream, purge rate is 8% of vapor recycled stream, okay, that information. And 70% of liquid stream goes to distillation column. We may need to put a little more new unit block there, it's called splitter. And distillation column, all information is given. So by given this information, let's try to learn our simulation. Now, when you practice, okay, as you can see, we connect more unit blocks. So we learn, for example, so far we learn reactor, okay, we learn distillation column, but we learn flash separator. We learn new thing today, for example, in this case, heater, and this one is a splitter, and this side the streams. So as you can see, our process of flow sheet becomes a little more complex and complex. How do you deal with this complex flow sheet? The best way, you go little step by step. Draw the flow sheet and do simulations step by step. So I will show you that way, how you deal with this complex flow sheet. Any questions so far? No? Chemicals with English unit, because all units are given in English unit, so I choose chemicals with English unit. Component, if you look at hydrogen, nitrogen, methane, benzene, cyclohexane. Great. Next, specify property method. So if I go here, I will check the method assistant. Okay. So if you go method assistant, let's look at it. Specify component type, chemical system. We are working on high pressure today, so I will say system at high pressure, yes. Then the method assistant recommend equation of state-based property method. For example, PRWS, Peng Robinson, Wang Sandler method, PSRK, predictive SRK method, or SIK, Soabe-Reddy-Kong equation of state. Okay. We look at SRK Wednesday, right? Yes? And SR forward. So, method system recommend this kind of property method. I will choose one of them. Maybe we can work on SRK. Soabe-Reddy-Kong property method. SRK, if you look at here, is called water method, the default is a steam table. No, so steam TA is a steam table. But SRK method, when they developed the equation, they used steam MBS table. So if you just learn with a steam TA, you will get some warning saying, SRK method is based on steam MBS table. What is a steam MBS table? It's a little modified steam table conducted by NBS, National Bureau of Standards. The National Bureau of Standards, they developed a new steam table in 1984. The SRK method is based on steam MBS table. Steam TA, basic steam table, 1967 steam table. Okay? So you choose SRK method, you just run the simulation, you will get warning, you come back here, choose a steam MBS table. Now we have to take care of binary interaction parameters in this course. The split, estimate missing parameters for unit path. That's enough. But we have learned how to use data available from NIST, the homework body. Okay? Great. I think we are in good shape. Who work every day 2 to 3 hours for this course? You are in good shape, I can tell you that. Who is not? Chase. If somebody will practice 2 to 3 hours per day for this course, what do they need to do? Practice how long?
3 to 4.
No.
2.
Oh, no, not enough.
What is it?
All night long.
1.
No, very weekend. Huh? If you haven't practiced enough, 2 to 3 hours per day, it's a good time. Saturday, Friday night, Saturday, all day long, all night long. You can practice, That's what you said, James, you practice all night long. You know? Anyway, let's go. Process flow sheet. If you have laptop, you can open the process flow sheet. I think a little fast. Okay, we have a heater. So if you go exchangers, there is for heater, and next one is for shell and tube type heat exchanger. Simply it's a heat exchanger. Right? So let's use heat exchangers for heater, heat exchanger. Right? We want to preheat or feed stream. And then if you go reactor, okay, we are familiar. We use R-stoic reactor today. When I say step by step, just learn up to here. Always, reactor is very important unit block or unit operation. So learn up to here, make sure everything works. So let's go step by step. We have 2 feed streams. Okay, H2 feed stream, hydrogen, and we have benzene feed stream. Preheat. This one, reactor input stream, reactor output stream. This is R stoichiometric reactor. Do not draw every unit block at the first time. Just up to here. Let's spectral up to here. For next, okay, I am working on benzene feed stream input specification. So if you look at, this is really, so please help me. So if you look at this slide, benzene feed stream input specification, hydrogen feed stream input specification. See? So I need your help. Benzene feed stream. 1
mole fraction.
know the temperature first. Temperature, pressure,
100.
total flow, 100 pound mole per hour, and mole fraction, composition, mole fraction is given, benzene is 1 in. Okay? Can I go a little faster? I am working on hydrogen feed steam, 120 degree Fahrenheit, 335 psi, 320 pound mole per hour. And composition is given by mole fraction. Hydrogen is 0.945, nitrogen 0.005, methane 0.05. Okay, we are working on heater. Heater 300 outlet temperature and pressure is 330 psi. All given. Our stoic reactor, so let's look at the reactor, 400 degree Fahrenheit. And pressure drop is given 15 psi. Lucia is looking at it. Olivia or Lucia is there. So the information is pressure drop 15 psi is given. How can we deal with the information here? Okay, so look at this one in. So we are working on R stoic reactor. What is the requirement here? Okay, it requires temperature input and pressure input. Yeah, that's required. If you look at our PowerPoint slide, what information is given? 15 psi pressure drop is given. So we are going to use that information for this designing. How? Here 15, that means the reactor pressure is 15, but the information is pressure drop information is given. Anyone understand? Jace.
Is it the inlet pressure, the 335 minus 15?
Okay. So inlet was 330, okay, minus 15, then maybe what do you need to put here? 315, that's a good approach. Pressure drop 15 is given. You can put 315 here, or there is other approach. Wonderful. Bailey, see, Bailey answer always correct answer. Bailey answer what I'm looking for. Bailey says negative what? Negative what? Wonderful. Negative 15. Pressure drop, you can use negative sign. In Aspen, I love negative sign, remember? So, pressure drop 15 psi, negative 15. Then, okay, let's continue. So, we have that information, pressure drop, we can check later. Now, reaction, as you can see, if you see, our reaction is benzene react with hydrogen, produce cyclohexane. Now, theory, we need to take the role of coefficient. Let's see. Come on. Give me answer. Coefficient. Benzene is 1. Hydrogen is 3. 1. Chemon is very quiet. Important thing is, do you know or not? That's important. You are quiet, somebody is quiet. But you know or not? That's important. And fractional conversion is given, which is 0.998% conversion rate of benzene. That information is given. Oh, we can run the simulation. But what we are interested in, cyclohexane mole fraction. So I go set up report option directory and then go swing tab. I click mole fraction in because I am interested in mole fraction. So let's look at it. Yes. Now we can look at it maybe swim summary. The last swim in this case reactor output stream, what we got? We got 82.8% cyclohexane purity, and then the cyclohexane production rate is 99.8 count mole per hour. Right? That's what we got so far. But if you look at this one, if I look at it, maybe temperature profile, pressure profile, maybe we can look at it pressure profiling. So if you see, input stream to the reactor, pressure was 330. We used that the pressure drive information. As you can see, output stream from the reactor is 315 psi. Okay? Yes? Good. So far so good, then we can continue to add more unit blocks. So next one is flashy separator, flashy 2 separator, so add flash 2, and then we have splitter. So if you look at the model palette, mixers splitter, the second one is F split. We have 2 splitter, new unit block, very simple, 2 we add. Now if you look at this splitter, the direction either right way, so if you right click, you can rotate this icon to left or right or horizontal. I rotate icon to facilitate to connect my stream. So if you look at here, I have input stream to this flash separator. I have vapor stream. I have liquid stream. Okay. And we have purge stream from this stream and recycle stream. Initially, do not connect to recycle stream yet. Do not connect to recycle stream yet. But let's go for the simulation. Let me type. This one is flash separator. This is F to vapor stream, F to liquid stream, and I can say this is a splitter. ST1, ST2, this one liquid recycle stream, and this one is vapor recycle stream. This one is purge stream. This is feed stream to distillation column. So step by step in. So let's go next. Okay, we are working on flashy separation. So flashy separation. Okay, temperature 120, and pressure drop is given 5 psi. Lucia? -5. Wonderful. That's how you learn little by little. What? Little by little accumulate, become intermediate simulator. Okay? Now we are working on splitter or split. Okay? So we are working on split 1. If you look at here, there's a specification, split fraction flow, limit flow. We can use a split fraction. And how much it goes to purge stream? 8%. So 0.08. We are working on SP2. 70% go to distillation column, 0.7. And I choose split fraction. That's enough. Run the simulation. Why not? No warning, no error. Yeah? So far, no warning, no error. Let's see. Hey, what do you think is our next step? Just go next. We are already done up to here. So nothing else. Now, from this flow sheet, what do you think is our next step? We learn simulation, no warning, no error. Clara. Add a distillation column, okay, that's a good choice. What else? Recycle. So, why now? We did not connect recycle recycle streams yet. But as you know, okay, I will show you it. As you know, if I run simulation, I got no warning, no error. So make sure no warning, no error. So next step, connect to recycle stream. Oh, let's do it. Let's connect to recycle stream one by one. I connect this recycle stream. Okay. Well, let's look at it. Oh, no warning, no error. Then let's connect this recycle stream. What do you see? Errors? I don't see errors. What do you see? Warnings. How many warnings? Wow. Clear looks so happy. Lucia, Clear looks so happy. I got warnings, they are happy. Why? What's going on here? Huh? I got warnings, you guys are happy. Let's see what kind of warnings I got. Warning. Total flow is 0. 0 feet block. I got some warnings. Well, sometimes you can ignore warnings. Well, if you are not happy, we need to fix these warnings. So whenever you're dealing with the recycle stream, I give you quick summary. What you can try? At least you can try 3 different approaches. Whenever you are dealing with recycle stream, you can increase number of iterations. So you can write down. You can increase number of iterations. What does that mean? How Aspen works? Aspen does sequential modular iteration calculation. Iterative calculation. So sequential modular, what does that sequential modular means? These are moduling. Okay? Just go step by step calculation. Okay? One time calculate, second time iterative calculation. It's called SM calculation. Sequential module iterative calculation. Now, if you go to convergence folder on the navigation pane, okay, you can check convergence, you get better information in. So if you go to result, here history, okay, then how do I do this iterative sequential modular calculation? Aspen choose a tier stream. This is called tier stream. What does that mean? So if you look at this flow sheet, we have kind of loop, vapor stream loop, liquid stream loop, corrected loop. So what Aspen does, within this loop, means with the recycle streams, Aspen choose a stream. In this case, Aspen chose R in stream, reactor input stream. Aspen chose R in stream as a tier stream, disconnect the stream, and then do the iterative calculation. 1, 2, 3, up to 1,000, even 10,000 iterative calculation, and calculate 2 consecutive calculations and see the maximum error divided by tolerance. In Aspen, tolerance default is 0.0001, 4 decimal point. Calculate consecutive iteration, compare the first iteration, second iteration calculation, and again maximum error divided by tolerance. If the absolute value of this maximum error divided by tolerance is less than 1, then the simulation converges. Yes? So if you look at here convergence, what Aspen chose as tier stream, Aspen chose R in as tier stream. So if you look at, we have this vapor stream loop, liquid stream loop, Aspen chose this R in stream as tier stream. But chemical engineering, and as chemical engineers, intuitively, what is the recycled stream here? Come on, speak up.
I don't know if I understand the question.
So whenever you have recycled stream in the flow sheet, Aspen choose a stream, any stream within that loop, and then Aspen choose any stream within that loop, and then use that stream as a tier stream. And how does a tier stream means? Tier stream, you disconnect or open the loop, and then do calculation. What is the advantage of tier stream? You disconnect this recycle loop, it facilitates calculation. So simply, why you open this loop to facilitate calculation? That's the purpose of tier stream. So Aspen choose R in stream as tier stream, disconnect this stream, do the iterative calculation, compare the previous calculation and current calculation. See, the maximum error divided by the tolerance is less than 1, then convert it. Yes? So, Aspen chose R in stream as a recycled stream, in other words. But intuitively, what are the recycled streams in this project?
Vapor and liquid recovery streams.
Yes. Intuitively, vapor recycle, liquid recycle streams are here through our recycle streams. We can see Aspen sometimes is Aspen is very smart, but sometimes it's not that smart when you deal with recycle streams. Aspen just choose R in stream. The reason is reactor is very important unit operation. So R in stream as recycle stream Aspen chose. But if you look at this flow sheet, these two streams are recycle streams actually. So, as a user, we can define these recycle streams ourselves. What does that mean? If you go here, convergence folder, there is for tier folder, you go here, and you can define your own tier stream as recycle stream. So in this case, we have vapor recycle stream and liquid recycle stream. Make sense? Okay? Let's reset. Maybe we can run the simulation. What do you see? No warnings, no errors. Huh? So first time I mentioned, first try to increase number of iterations. What does that mean? If you go options, okay, the default method for this tier stream, there are 4 different methods. It's for Wegelstein, direct, Boyd, Newton. We will look at it next Monday more. Okay? And if you go method, the Wegelstein tier stream method is default. And default number of iterations is 30. When I mentioned you can increase the number of iterations, you can increase this number. Okay? So that's the first approach. The next approach, you can check the tier stream, you can define your own tier stream. Okay? The next approach, okay, maybe you can change this default method. We have 4, especially for tier stream. This is convergence method. There are 4 different convergence methods. Maybe you can try this one method for tier stream. And so those are 3 approaches. So as I said, do not worry for today. You just look at it, and the next Monday we look at all the depths in. So far so good. We got no warnings, no errors by defining tier streams. And now we can explore the distillation column. So let's go distillation column. In this distillation column, we have vapor stream. So I connect vapor stream, not liquid stream. And we have liquid stream. So we look at attention. Okay. And I will say red plus vapor. red truck liquid. What we are interested in, we want to get maximum cyclohexane production from the bottom stream of distillation column. It's a purity of 99.9%. That's what we are looking for. So let's go. Number of stages given 15. Condenser. What condenser do you think we need to choose? Partial vapor, because we have vapor streaming, so you choose partial vapor. Total condenser means liquid stream. Okay, reflux ratio is given 1.2. Now, our target is, our objective is to get the maximum cyclohexane production rate from the bottom stream of distillation column. Keep in mind, always keep in mind, what is our objective? That's our objective. We are interested in bottom stream flow rate. Bottom stream. So maybe I can use that information for operating specification. I can choose bottom stream. We don't worry about this rate. We worry about bottom stream. What information is given? Bottom stream is not given. You guess any value and start simulation. Guess. So we can find out it. Why? That's what we are looking for. Stage feed stream, stage A, pressure is 200. Those are all given. Just run the simulation and see what happens. No warning however. Let's check what we are looking at. We are looking at red drop bottom stream. So red drop liquid this stream. That's what we are looking at. Cyclohexane purity should be 99.9%. Well, what do you see, Weston?
99.7?
99.7%. Why? Because we chose the bottom plate 100 pound more per hour. Maybe that's not true. Huh? We have to meet consumer's demand 99.9%. What can we do? What can we perform? Find out. So, okay, but we need to perform some tool or function here. Kind of setting. What kind of setting can we apply? Steve, come on. Design spec. Yes. You use this. Or do you want me to do it? Let's go quickly. We use design spec. So if I use design spec, I can go quickly. So I will name it, define means we are the cyclohexane mole fraction should be fixed, which means cyclohexane mole fraction are left to liquid stream. Component cyclohexane mole fraction. What does that mean? This cyclohexane mole fraction should be 99.9%. I want to be actually 3-4 decimal point. What do we vary here, darling? Bottom rate. So what is I choose block variable because bottom rate. If you look at here, I give you information. If you look at here, we are changing this value. These are block variable, okay? Because it's available block. In this case, red block. And bottom slate is more B, I think. So if you go here, over your mouse, bottom's more low flow rate. Oh, I like it. Initially, I chose 100, so maybe 10 to 300 maybe. Let's learn the simulation. Okay, we got error. So who is smiling? So if you look at here, what kind of error we got? Error, red prop not converted in 25 outside the loop iteration. The default iteration is 25. Can I increase the iteration? You go red prop block. Okay, there is called convergence directory to our folder here. Convergence. So convergence because red prop is not converged in 25. Why is maximum iteration default is 25? Maybe you can increase this one. 100 or 200, increase number of iteration. Oh, who is smiling? Oh, Weston, thank you. Hi, I love, okay, Lucia. Oh, Brian, I like it, thank you. You go stream summary, what we are checking RLF liquid stream, 99.9%. We get 78 mole per hour of cyclohexane production. Great. When I say homework, you attach this stream table into your flow sheet by clicking this one. Okay? And I said red circling, I will show you everything. So what I mean red circling? The reason the red circle because to our TA, we go lines, red circle may be line this largely, and then you put this red circle into your answer here now, somewhere like that, so that TA can easily find out your answer. That's what the red circle means. Any question?